Hello fellow engineers. In today's video we're going to go over a heat transfer problem dealing with a journal bearing. The primary function of a bearing is to reduce the wear as much as possible by bearing a load between a rotor and a casing. The way we're going to set up this problem is, with the bounding surfaces being much smaller than the radius, we can solve this problem using the model for flow between parallel plates. For this problem, we will consider engine oil is being used in the bearing with a gap of 0.4 millimeters for the length between the plates, with the top surface moving at 15 meters per second to simulate the rotation of the bearing, while the bottom will be stationary, simulating the casing. We will use the following information to calculate the actual numbers that I will be showing you. With the temperature of the top plate being 60 degrees Celsius, the bottom plate being 20 degrees Celsius, with our K being 0.1444 watts per meter times Kelvin, our mu is going to be equal to 0.2177 kilograms per meters times second. Here you can see the diagram of the parallel plates model. The placement of the coordinate system origin is very critical in solving this problem. I'm going to place the coordinate system on the bottom plate because it is stationary and it does not move relative to the top plate. The method I will be using to solve this problem will be the systematic methodology. This method will look different from just finding an equation that works and plugging and chugging. This method will help you take the original equation and derive the governing equation for this specific problem. For this, we need to create a list of assumptions. The first one, we can assume it's one dimension. The reason we can assume this is because the flow is going in one direction. It is not going in the x direction and the y direction. It's just going in the x direction. For our second assumption, we can assume a steady state, which means the flow rate stays constant throughout the time. And the third assumption is the pressure gradient is equal to 0 because we made the assumption that it is steady state. And assumption number 4 is we will ignore gravity. Since we are dealing with such minute distances, gravity has no effect. And our fifth and final assumption, velocity in the y direction is equal to 0. The reasoning for this is no matter where you go in the gap, the velocity stays the same. There is no change. With these 5 assumptions, we can use the Navier-Stokes equation and eliminate the components that we do not need to get the governing equation for the velocity profile of the engine oil. So the first step is we're going to go and look at assumption number 1. We know we can look at assumption number 1 and know that the partial derivative of u with respect to x will be 0, and the partial derivative of u with respect to z will also be 0. And on the other side of the equation, we can go and x out on the partial derivatives in those same directions. Using assumption number 2, we know it's steady state, so it does not change with time. Assumption number 3, the pressure gradient is 0, so the pressure function goes to 0. Assumption number 4, no gravity, so the gravity function also goes to 0. Then the velocity in the y direction is 0, so the v in the partial du with respect to y goes to 0, leaving us with the equation of mu times partial derivative squared of u with respect of y squared is equal to 0. And then we can divide mu by both sides, which just leaves us with the derivative squared of u with respect of y squared is equal to 0. When we integrate this derivative twice, we get u with respect of y is equal to constant 1 times y plus constant 2. Now we have a velocity profile, but the only catch is we have 2 unknown constants. This is where boundary conditions come in. We're going to assume boundary condition number 1 is the bottom plate, and where our coordinate system is, y is equal to 0, and also our velocity at that point is also 0. When we use these boundary conditions, we can get 0 is equal to some unknown constant of 1 times 0 plus constant of 2, which tells us that the constant 2 is equal to 0. Then we can go to boundary condition 2, which is the top plate. The y will equal to L, the length of the gap, and the velocity will be equal to the speed of the top plate. When we have that, we have Vt is equal to L C of 1 plus 0. And when we solve for C of 1, we get C1 is equal to velocity of top divided by the length. Now that we have the constants, we can plug those back into our velocity profile, and we can get a equation of u with respect of y is equal to v of t divided by L times y. Now that we have the velocity profile, we can go and find the temperature profile between the bounding surfaces using the conservation of energy equation. This equation of energy conservation might look a little bit different than you are used to. In this problem, we cannot ignore the viscous shear stresses, where the viscous precipitation function is provided at the end. Going back to our assumptions, we can remove the parts that go to 0 and have no effect on our profile, which nets us the following equation that will give us our temperature profile. When you simplify it, we get a second order differential equation. Then we can take the derivative of the velocity profile and put that into our temperature profile for us to find our temperature profile for any location in this problem. Once you take the differential of this problem, we get the following equation. Just like our velocity profile, our temperature profile is also dependent on where in the gap we are looking at. And again, just like our velocity profile, we are given two unknown constants, which we will repeat what we did with our velocity profile by setting boundary conditions. Again, boundary condition 1 will be the bottom plate, so y is still equal to 0, and our temperature will also be equal to the temperature of the bottom plate. And when we plug that information into our equation that we just solved for, we get the following constant of C4 is equal to the temperature of the bottom plate. For boundary condition 2, which is the top plate, y is again equal to L, and the temperature is equal to the temperature of the top plate, which nets us our constant 3. Once we have both of our unknown constants, we can put those back into our original equation, which gives us our temperature profile. Now that we have the temperature profile, we can find the location of the max temperature. Remembering your calculus days, when you take a derivative and you get 0, you know that is either a max or a min on that function. In this problem, we know that this is a parabola. When we get a derivative of 0, that is the max temperature. So we know that dt with respect to y is equal to 0. So we take our temperature profile equation and we derive that equation, giving us the following equation that you see before you. With dt with respect to y is 0, that becomes 0 equal to this. Now we solve for y. This equation gives us our max location for the max temperature. And when you plug in the information that was given in the beginning of this problem, we get a location of 0.247 millimeters. We know this makes sense because it falls within the gap range. Now that we know where the max location is, we can now find the temperature at this location, which gives us a temperature of 84.76 degrees Celsius. And the last thing we can find is the heat flux for the bottom and the top surface. As you can see, the heat flux equation is very simple and quick to solve for. which gives us a heat flux of 161.23 kilowatts per meter squared. We will use the same method for the top surface, which nets us a heat flux for the top of 75.62 kilowatts per meter squared. What I like so much about this method of solving heat transfer problems is it gives you the governing equations for any problem using just two equations. With the governing equations for this problem, I can work and change the velocity of the top plate. I can change the temperatures, the gap length, any of those numbers I can change, and I can get the new numbers without going back and solving this problem all over again. This is a great tool to analytically solve a problem multiple times in a very short order. Now, in real life, on the job, will you be doing this by hand? Hell no. You'll be using computational fluid dynamics, most likely. This is a great problem to show the fundamentals and understand the concepts of heat transfer. And I can delve into more about the heat flux and heat transfer if you want. Till the next time, stay safe, and remember, hit the like button, and if you haven't already, consider subscribing. Have a good night.